The slogan, what? I don't know. I'll have to think. This is problem 21. Okay. So this is what they show us. Oi, oi. Okay. Y-S. So that loop has a resistance of 0.230 ohms. It's being pulled this way at a speed of 3.4 meters per second. This distance here is 0.350 meters, right? Okay. And the first question is, actually it says calculate the total force required to pull the loop from the field, right? So what they do is they multiply, apparently the magnetic field is 0.450 Teslas, yeah? Right? So they calculate the EMF induced and they only use the length of this little stretch of the wire. Why is that? Why is that the only important part?
Because that's the changing, it's going out of the field.
That's the part, and then the way to think about these wire problems, right, is that that's the part that's actually crossing the field lines. The other ones are just sliding along the field lines, right? The wire has to go across the field lines, and the reason for that is that the way the force works is that we go like this. We go, okay, the positive charge is moving that way, magnetic field is into the page, and on this little segment of wire, a positive charge will actually be pushed upward, which, by the way, predicts which way for the current. Current's going to go, if it's going up this side, it's going clockwise in general, okay? Now, this part of the wire is not in the magnetic field, so there's no net force on the current, on the charge there, right? And this part here, basically the charge on this part of the wire is trying to be pushed that way as well, but it can't go that way because the wire doesn't go that way, okay? So that's how that works. So the first thing they do is they figure out the potential, right? So they do BVL, they figure out that the potential is this. Then they figure out the current, and they get that it's that many amps, yeah? Which is a wonderful thing, right? Okay? Then they figure out the force, right? And the force is going to be ILB. And which way is that force going to be, by the way? By the way, which way is that force going to be on this wire? Let's think about this. As I pull this loop out, I'm generating electric current. I'm doing work, right? So is that force going to resist my motion or help my motion? It's going to resist, yeah? The force has somehow got to be this way, so let's figure it out. Okay, if the current flows that way, right? Now we're doing ILB again, right? Current flows this way on that wire. Magnetic field is into the board. Which way is the force acting on that little chunk of wire? This way, yeah. So the force that's acting because of the current that flows is actually going to be this way. Isn't that cool? Yes?
You quickly go over the right-hand rule he used to figure out the direction of the current flow in the wire.
Yeah, okay. So let's go through the two right-hand rules, right? We're going to use them twice, right? First right-hand rule is the wire has positive charges on it and is being moved that way, right? Okay, so there's the motion of the wire relative to the field, okay? And for that rule, that's the QVB rule, right? So we put our finger in the direction of motion, magnetic field into the board, thumb is up the page, which means positive charge is going to be pushed upward in this segment of wire, right? And therefore it's going to go clockwise in that loop, right? So that's the first one. The second time we're going to use this rule is now we go, okay, as that thing is moving this way at 3.4 meters per second, there's a current of 2.328 amps going this way in the wire, right? Now, that is a current in a magnetic field. There's going to be a force on it, yes? And that force is going to be, well, let's do it. Current this way, right? Magnetic field into the board, the force is to the left. So as we pull that thing out, we feel a resistance force, and all is good. I'm doing work. Where's that energy going? Into the wire. It's heating up the wire. There's a current flowing. We could light up light bulbs, etc. Yeah, are we clear on that? Right? So this is a beautiful thing. Isn't that a beautiful thing? Yeah. And in fact, when we figure out this work, this 0.367 newtons, right? When we figure out that work should also equal the electric power generated, shouldn't it? I think it should, shouldn't it? So we ought to be able to calculate the energy two different ways. Way number one is that we ought to be able to calculate it in terms of whatever this force is times whatever that distance is, right? And they give the distance as half of 0.750. Let's just assume that it's half of that, right? Right, so half of that would be what would it be, 0.3750 meters. Is that half of 0.75? Yeah, okay. So that's half the distance. And so if we multiply this force here, right, by that distance, so 0.45 times 3.4 times 0.35, there's my voltage divided by 0.230. I've got this, I just want an unrounded version of this, right? And then I multiply that by, and that's my current, right? Okay, I multiply that by times 0.35 times 0.45, and I get this force. So 3667, right? We've got this thing. Now we can figure out the work, and the work is force times distance, right? So it's going to be this guy times this guy. Right, so that times 0.750 divided by 2. And that ends up being, so 0.3667 times 0.3750 is 0.1375 joules, right? How else can we calculate the work? Can we calculate the electric power? Could we multiply the power by time and get the work that way too? Shouldn't they be the same thing? In other words, shouldn't the work I do pulling that thing out equal the electric energy that we generated, right? So let's calculate that way, right? So let's go this thing here, right? The power is going to be I squared R, right? So it's going to be 3.328, all right, 2.328, right? Squared, okay? And I think I've got that in my A. I stored that in A. That's squared times 0.23 is the resistance. Right? So that's squared times 0.23. I'm getting 1.2467. And what's the unit of power?
Watt.
Right? Now, how do I go from power, that's joules per second, to energy? If that's joules per second, we multiply by time, right? Okay. So how much time did it take to leave the loop? Can't we figure that out? Isn't it just distance over velocity? Right? So the time is going to be just going to be 0.3750 over 3.4. That's our time. God help you if you're trying to like read this, right? Okay. So I'm going to store that in B, right? The answer I've got there. And so 0.3750 divided by 3.4 is the time. The time it takes 0.11029 seconds to leave the field. By the way, the problem didn't ask any of this, but the test asks questions like this, so I'm just going to do this, and then we'll do it again on the skill set, right? So we've got the time, we've got the watts, right? And if we multiply joules per second by seconds, we get joules, right? So this times this is equal to, I get 0.1375 joules, right? So this is a profound thing, or maybe it's very unprofound, is that if we figure out the force times the distance, we get 0.1375 joules. If we figure out the electrical power generated and multiply that by the time we generated that power, we get the same exact work. Is this conservation of energy or what?
Yeah, it is.
Might be what, you know. What if it's or what? You know, it's like, is it this or what? What if it's what? And what is what, right? I mean, I don't know.